Good evening, everyone. Welcome to another of the Parliamentary and Scientific Committee's webinar discussions. It's great to have you all with us. And I would really like to welcome our distinguished panel of speakers who are going to help us explore coastal waters this evening. It's great to have with us Matthew Parr, who is Director of Strategy and Regulation at Tideway. Matthew, thank you for joining us. Dr. Helen Finley, biological oceanographer at the Plymouth Marine Laboratory, and Professor Richard Thompson, OBE, Professor of Marine Biology and Director of the Marine Institute at the University of Plymouth. The three of you are very welcome, and we very much look forward to what you have to say. Now, before I come to our first speaker, who is going to be Matthew Parr, just a few sort of housekeeping rules. If you're not making an active contribution, can I ask you to remain on mute? It just improves sound quality. If you want to ask a question at any point when we get to the question and answer session, can you please use the Q&A function within Zoom, not the chat button? Sometimes those get moved. If we have all the questions in one place in Q&A, then we can make sure that none of them slip through the net. Lee will then marshal those into a suitable order and let me know. I will then go to each person wanting to ask a question. I'll say their name. Ben will then unmute them and the person will be able to make their contribution in person. Now, unless I've forgotten anything, and I don't think I have, we will start. So, as I say, it gives me great pleasure to welcome Matthew Parr from Tideway, who's going to talk on, give us an overview of the work of Tideway, which is an extraordinary project, which I'm sure he will tell us all about, and the contribution it can potentially make to improving our coastal waters. Matt, over to you.
Thanks, Stephen. Hopefully you can now see the slides on your screen. Have they appeared? Yep, I'm getting a nod.
Brilliant.
Thank you. Well, we can get started then. So yes, a few slides I'm going to talk around today. When it was around coastal waters, I thought, well, we're slightly fringe to this because really the Tideway project is dealing with tidal River Thames. But what I plan to do just in the next few minutes is go through the slides pretty quickly about a really major infrastructure project that's currently underway in London. I think now Crossrail's finished probably the biggest infrastructure project in London, and the progress we're making. But first, a bit of history, which I'm sure a lot of you are well aware of. This is a picture of the River Thames, and you'll see that the lost rivers, the Fleet, the Tyburn, Westbourne, etc. We really have to go back 150 years or so to the Great Stink in the 1858, when, in fact, Parliament had many questions about how they might deal with the Great Stink, including soaking their curtains in chloride and lime, thinking about even leaving Parliament, leaving London. As it happens, they asked Sir Joseph Bazalgette, the chief engineer for London, to look into the solution. They managed to pass a bill. I think it was certainly the quickest at the time ever. In 18 days, they created and passed the bill. And Sir Joseph Bazalgette effectively came up with a solution to solve, at the time, the pollution that we're seeing in the Thames, the tidal Thames. And effectively, those are the black lines that you see running from west to east. These are large interceptor sewers, which are going to intercept the sewage that was running through those lost rivers and take them to the East London, effectively where they'd be discharged. When he undertook his planning, the population of London was about 2 million. His planning remit was for 4 million. But now when we come to 2019 and beyond, it's beyond that. It's double and more than double that, so 8, 9, 10 million. So the problem we have at the moment is that there are about 40 million tonnes in a typical year of discharges, sewage discharges into the River Thames. Regular spills, it takes about 2 millimetres of rain in London before you can get discharges of sewage. So the solution was actually three parts of the solution. On the east of London were upgrades to sewage treatment works. The second part was the creation of the Lee Tunnel, which is, if you can see at the top right of the diagram, in a sort of pink purple bar that goes from west to east, running from Abbey Mills to Beckton Sewage Treatment Works. So that's been constructed by Thames Water. And the third and the largest part of the project was the Thames Tideway Tunnel, which is, in fact, the main tunnel is 25 kilometres long. It's the purple, orange, and then the yellow line that stretches largely along the River Thames. And its main job is to intercept the majority of discharges that would go into the River Thames. So remember, I talked about that 39 million tonnes a year in a typical year, but about 95% of that volume would be collected. There'll still be discharges, but we think about 4 a year, but typically they will be the least polluting because it will be highly dilute, the sewage. It's largely be runoff, rain runoff. So that's effectively the job we needed to do to build the Tideway Tunnel. Effectively, there's probably scope of a different presentation, but a new delivery model was created for it. It's funded by water customers, but the finance comes from the private sector. Effectively, there was procurements for who was going to run it. There was a procurement for the lowest cost of finance to deliver this project. The overall bill impact was going to be between £20 and £25. You know, we are at the lowest end of that in terms of our current forecasts. So I think the way it was delivered using private finance has been really beneficial. Some stats and figures about how big the project is. The width of the tunnels, you can fit 3 double-decker buses down them, are shafts which run. The shallowest ones are in the west, our deepest ones are in the east. The gradient drops 1 metre for every 800 metres along the tunnel. So between 30 and 66 metres deep. And the capacity is 1.6 million cubic metres. And effectively the way it will work is when there's a significant amount of rainfall in London and they would have discharged into the river. This is a sort of a cross section of the site at Victoria. We've got many sites across London. Effectively, you'll see on the right-hand side, the sewage, rather than discharging into the river, it flows down a deep shaft. There's a vortex to try and remove some of the air. And then effectively there's a small connection tunnel which is running right to left, and then the main tunnel. The main tunnel typically runs under the middle of the River Thames for most of the journey. I guess this is, you also see there's a site here. We've a number of different sites across London where we've created new land. Effectively, cofferdams have been created, and you'll see if you walk along the North Bank that the site of Victoria has one of those. It's still a construction site, so the architectural landscape hasn't gone in yet, but effectively there will be new permanent land there, and presumably a very good view of the fireworks at New Year's Eve. So where we've got to, we're 78% construction complete. We finish all our tunnelling, we finish all of our shafts, our deep shafts. We think there's probably another year of construction to go, and then the long process of commissioning will start, which involves commissioning individual sites as well as the overall system. We're working incredibly closely with Thames Water, who are a separate regulated and separately owned company, but we co-locate with them and working very closely through the construction and commissioning phases. And we think the project as a whole will be operational by 2025, so that's on track still. As I said, we are privately financed. We've fully funded the project for the whole of the construction phase already. And something that I'm very proud of, and I was involved in right at the beginning of this project, you know, it's a £3 to £4 billion project, is we really focus about how we can maximise value for money in its broadest sense right at the beginning. And we established some legacy commitments which we monitor and we publish, and we've got 90% of those legacy commitments are on track. I thought I'd include some photographs people like to see, you know, the sites. This just gives you an idea of the scale. On the left-hand side is one of the bottoms of one of our deep shafts. What you'll see coming in is a connection tunnel. And on the right-hand side, effectively, when you do the primary tunneling, we then put in a secondary lining. And so why this looks so smooth, this is after the secondary lining's been put in. And the secondary lining helps structurally. The tunnels need to last a minimum of 120 years, but it also helps with leakage and seepage, so sewage coming in and out of the tunnel. This is a tunnel boring machine. You'll see tunnel boring machine on the left-hand side. It was brought in by this barge, and it was effectively lifted onto site. And you'll see on the right-hand side a tunnel boring machine. That's before it started tunneling. I've got to say, that's a very clean-looking head of a tunnel boring machine. And there were 6 tunnel boring machines, each of them named after famous women of the past. And 5 of them we will remove, and 1 of them we've had to bury in one of the side tunnels. I talked about the legacy commitments. There were 5 limbs to this: the environment, which obviously a really core driver of the project. The UK were failing the Urban Wastewater Treatment Directive, so it was under prosecution by Europe. So that was a main driver. But we set out our commitments around environment. Health and safety and wellbeing is absolutely #1 priority on our project, and there are various commitments there. But also about how we can support the economy. So we've invested heavily in Moor by River. So beyond our planning, our DCO, our planning commitments, we invested an additional £50 million in terms of taking more of the material in and out via the river rather than lorries. So hundreds of thousands of fewer lorry movements on the River Thames, on our roads, London roads, which is obviously better for congestion, better for road safety, and so on. And we've also helped train up a lot of the people who work on the river. There's clearly a strong skills and employment legacy around people and the places. So this is an illustration of one of our sites. I think this is King Edward's Memorial Park once we finish. So a lot of architecture and landscaping activity that needs to be done. We're not at that stage yet. So this is the final slide, and I put this in really because I'd rapidly try to go through all these slides, but it was a clear remit that we needed to go out and build a very large tunnel to do a specific job to intercept sewage into River Thames. But we had an opportunity to do far, far more than that. And that's what we tried to do in terms of our approach and our legacy commitments, but also the way we engage with Londoners, London and Londoners, to try and reconnect London with the River Thames. So I shall stop there. That's the end of the presentation, Stephen.
Brilliant. Matt, thank you very much indeed. Absolutely extraordinary and fascinating project, and sort of a worthy legacy to Joseph Bazalgette's ambitions of 150 years ago. I think it's a fitting update. I'm intrigued. I've got a few questions actually. Firstly, when this is completed and opens in 2025, do you believe that the public, Londoners, we here in the House of Commons, will see a difference in the water? Will we be able to see an improvement in it, or will it just be something if you sampled it, you'd know there was an improvement?
So, I think the answer would typically be the River Thames is a silt-based river. So it's a brown river, and you know, whilst it will be a lot cleaner, and you know, it's fair to say that river health has rightly gone up the agenda over the last few years. And I know the water companies and the Environment Agency are looking closely at monitoring. And this is not about necessarily what we're doing, but across all rivers, and providing live information to those people who are interested in it or want to use the river for various purposes. So I think there will be, in years to come, a lot more information about the live river health and river quality that will be a lot more visible to people.
Fantastic. And of itself, it's an extraordinary construction project. You know, the scale of it, right on the doorstep of London, or right in the heart of London, I should say. What sort of community engagement did you undertake in terms of using the project itself to inspire a future generation of potential engineers, whether they civil or others? Because, you know, seeing something like that, seeing a tunnel boring machine up close and personal, can have a sort of transformationary effect on people.
Yeah, so I thought you were going to go a slightly different place with the question. Actually, it was our broader engagement with stakeholders. And I have to say, I mean, I've been on the project for over 10 years now, so I was lucky enough to be in the development phase as well, and the shaping phase. There was a vast amount of engagement with Londoners going back around even way before planning, in terms of the potential benefits, but also the site locations, which are not obviously easy conversation to have with people. But in terms of inspiring Londoners, I think a huge amount of our effort is about engagement, and it's engagement through community liaison working groups. We have a TTT forum which engages all of the impacted local authorities as well as various different regulators. But we also engage with STEM. So there's a lot of us who are engaged with the science, technology, engineering, maths, in terms of engaging with schools and to try and inspire people there, and also work with various charities. So we all have some volunteering days that we can spend with colleges or schools. Certainly one of the most rewarding moments I've had on the project was working with a group of sort of 50-year-old kids on an engineering project.
Brilliant. And have you actually taken groups down into the tunnel itself on site?
That is less easy to do.
Shame.
Because of safety reasons. Actually, there's many people who work on the project who haven't yet been down the tunnel, but we do have a sort of headsets you can wear, so you can virtually go down the tunnel even if you can't actually go down the tunnel. So we take that around so people can experience what it's like and be on a tunnel boring machine effectively.
Fantastic, brilliant. Matt, thank you very much indeed. Very interesting presentation. Right, we will move on. We're going to move now to Dr. Helen Finley, who is going to talk to us about coastal ocean acidification. Helen, welcome. Thank you for joining us. Over to you, 10-12 minutes or so.
Thank you very much, and thank you for inviting me to discuss the issue of ocean acidification around our coasts today. Just to check everyone can see the screen okay and hear me okay?
Absolutely.
Brilliant. So so I'm Helen Finley from Plymouth Marine Laboratory. I'm also on the Executive Council for the Global Ocean Acidification Observing Network and the chair of the Northeast Atlantic Ocean Acidification Hub of the Go On Network. So just so that we're all on the same page briefly, carbon dioxide is naturally taken up by the oceans. The oceans have taken up about 25% of the CO2 that we've emitted into the atmosphere since the Industrial Revolution. CO2 reacts with water to become part of the marine carbonate system, which over geological timescales can be buffered by weathering processes. However, we've been adding too much carbon dioxide too quickly, and this is shifting this marine carbonate system, resulting in ocean acidification. So that means the hydrogen ions are being released, causing oceans to become more acidic, and the carbonate ions in the marine carbonate system are being reduced. So that essentially makes seawater, we can think of it as becoming more corrosive to calcium carbonate minerals, such as exposed shells and corals. So we mostly hear about ocean acidification, I'm sure many people have, on a global scale, whereby the global ocean surface ocean has an average pH in pre-industrial times around about 8.2. You can see this in this map at the top left here. And pH has decreased on a global surface scale to around about 8.1 by the year 2000. And we've got more data that show by year 2020, the ocean was on average around about 8.05. So it doesn't sound a huge change in terms of pH. pH is on a logarithmic scale, but actually that means that it's 43% more acidic now than it was in pre-industrial times. Now, this matters because organisms need to maintain their internal acid-base physiology. So just like humans, where any small change in our blood pH can cause serious illness, marine organisms rely on the external environment as well as their internal ability to maintain those internal pH conditions as well. So any change in this carbonate system, the pH or the carbonate elements of that, can affect their internal acid-base regulation. In addition, any organisms that produce these calcium carbonate structures, like shellfish or corals, potentially are at greater risk because if they are exposed to this kind of corrosive condition in the future. So as ocean acidification stress increases through time, if energy is limiting, we expect to see many negative effects starting to occur. At a global level, moving into the future, ocean acidification is tied to CO2 emissions. And the more CO2 emitted, the results in more acidification. So with levels reaching down to 7.7 or below, depending on what scenario we end up following. You can see the Paris agreements, low emission and the high emission scenarios on this graph. Just to kind of give you a visual implication of what that means for some of these calcified organisms, these are normal blue mussels that you would perhaps go and eat at a restaurant. These shells have been exposed to different pH conditions. So you've got pH 8.1, 7.9, and 7.7. And you can see that the shells are starting to dissolve in these areas here. You can start to see they're kind of orange and less of this nice dark blue material on the outside. And going to extreme levels, you can see that they're almost see-through and breaking away. So that's what we're talking about when we're talking about exposed calcium carbonate being dissolved away. So these changes can have significant impacts on marine ecosystems, coral reefs, carbonate reefs, seagrass meadows, and pelagic food webs. But as I'm sure many of you are aware, most of these important habitats are in coastal regions, which is where it's much more complicated in terms of acidification, because we have lots of other factors in the coastal regions that can affect acidification. So rivers flowing in, changes in nutrient inputs, mixing, tides, other biological activity, all can potentially enhance or mitigate this overall acidification signal. So it's a very complicated region. And we know much less about the coastal regions and how acidification is manifesting in these regions than we do about the global ocean. We do know that these global rates of acidification are likely to lead to economic losses in the future. And this is an example of loss of production in mollusk shell fisheries across Europe. But we need to understand acidification at this local level, the coastal level, to improve our ability to predict these sorts of economic and societal impacts, and also to act to minimize impacts. So we recently completed the Ocean Acidification Assessment as part of the latest OSPAR Quality Status Report, which will come out next year. Here we assessed a number of time series across the OSPAR regions, and we found that the ones in the open ocean system, so around Iceland and northern Norway, the subarctic Atlantic, had very similar rates of acidification that we would expect to find in open ocean water systems around the world, and the same for warming patterns. What we were really surprised about was that when we started to look in the nearshore coastal environments, so around the Western Channel in particular and the Bay of Biscay, the rates of acidification were an order of magnitude faster than these open ocean systems for the past 15 to 20 years, which has never been really documented before and is of significant concern. So you can see in these graphs here, you've got the Western Channel and the Bay of Biscay have significantly faster rates of acidification and faster rates of warming. Now in the UK, we have two long-term sites up in Stonehaven off the east coast of Scotland and off Plymouth here in the southwest UK. And these are showing these enhanced rates of acidification at these coastal sites as well. And they also show that we have large amounts of coastal variability. So this is the variability that I was talking about because of the differences in freshwater inputs, the biological activity, things like that. Now, this variability is also important in the coastal region because it will affect how organisms can respond and how acidification manifests in the future as well. So for instance, I'll just stop this video, it always starts. In the future pH trends around the south, the European shelf are expected to continue to the mid-century and beyond, depending on what emissions scenarios we follow. Coastal pH will decrease by similar amounts to the amount that we've seen over the last 30 years or so. But interestingly, this level of variability means that over about 90% of the shelf seas around the UK are likely to become seasonally corrosive to these calcium carbonate minerals. So here I'm going to play a video, and it's from beyond 2050 to the end of the century. And what this video shows is that when the seawater is below 1 or red, then it's essentially undersaturated or corrosive to aragonite minerals. And aragonite minerals are a common calcium carbonate mineral that are used by mollusks, shellfish, and corals as well. So if it's blue, it tends to be okay. If it's red, it's bad, basically. And what you'll see is this goes through months, every month of the year to the end of the century. And you can see in January, we start off with a relatively blue ocean throughout the North Sea. So this is going from the southern North Sea here up into the northern North Sea just by Norway. So what we see is in these deeper regions is the bottom waters start to become undersaturated or corrosive relatively quickly. And you'll notice that as we move forward in time towards the end of the century, so by the 2090s, we're seeing the full water column is flashing red at certain times of the year. So especially in the winter months, we expect, here you've got December at the end of the century, nearly all of the water in the North Sea is undersaturated with respect to these minerals, making it much more difficult for these organisms to produce their calcium carbonate shells and maintain those shells. So we expect that to be a significant issue in the coastal regions around the UK. So oceanification is occurring globally, and it appears to be occurring at enhanced rates around our shores. And we need policy at national and local level to develop action to make sure we minimize the impacts of acidification. So the International Alliance to Combat Oceanification suggests that this can be achieved through 5 main mechanisms. And I'm going to go through those 5 here and how they're relevant to activities that are ongoing in the UK. So the first is mitigating the causes. So primarily reducing emissions. We know that acidification is directly tied to CO2 emissions, but we also want to be investing in renewables as with other aspects of climate change and more immediate low carbon options. We also need to be investing in blue carbon, and at PMO we're working on how seagrass, kelp forests and shelf fisheries can be included in nationally determined contributions and also carbon accounting. So this is really important for thinking about how we account for the carbon moving around in these different systems. We want to be investing in carbon dioxide removal technologies. Again, at PML, we're working on projects such as the BIS-funded Secure project, which will enhance the ocean's ability to take up carbon from the atmosphere, as well as alkalinity enhancement projects that could help reduce acidification. Secondly, we want to assess local vulnerabilities. So once we know the systems that are most at risk, we can manage co-stressors such as fishing, trawling, agricultural runoff, or sewage treatment. So it's great to see the London sewage improvements, because obviously that has knock-on consequences for some of these coastal impacts that will either enhance or kind of add to the acidification problem. And we're working again with people like DEFRA to look at how best we can make those sort of assessments. Thirdly, we want to identify local research and monitoring gaps. So this means investing in science, networks, and monitoring and capacity building. And again, we're working with people like DEFRA and the OA Alliance, as well as through the Global Oceanification Observing Network, to improve the UK's monitoring, feeding into things like the UK's environmental status, and the MMO reporting structure, OSPAR, and the United Nations Sustainable Development Goal 14. Fourthly, we want to build adaptation and resilience. So this is really looking at investing in adaptive planning, habitat protection and restoration. And again, this kind of feeds into this managing of co-stressors. But we're really, at PML, we've been working with a number of partners to use climate smart marine spatial planning. So this is where we integrate knowledge of the climate impacts. So this could be acidification, it could be warming, it could be a multitude of different factors going on, everything that we can kind of gather about climate impacts, and use that information to look at where the best places to put in MPAs or other maritime activities, so that we can really make sure that we're including those climate aspects where there might be multiple stresses, or there might be places that are refuges for species and things like that. And finally, education. So I'm going to sort of end on this one, but hopefully this sort of discussion will help to inform our next steps. So being able to communicate with yourselves and others, publics and stakeholders, it really allows us to be able to incorporate these sorts of actions into either existing or new policy frameworks. And we're hoping to continue to take those discussions forward, and hopefully we can help to reduce the impacts and these really quite surprising results of enhanced acidification in our regions. So I'm going to end there. Thank you very much, and look forward to questions.
Helen, thank you very much indeed. Fascinating, and a lot of stuff in there to take on board. A couple of questions, if I may. Firstly, just on the future projections, one of them said that the pH level could drop to 7. Now, from where we are at 8.05, which was a 43% increase from 1750, what would that look like in terms of an increase by the end of the century?
So 7.7 is about 150% more acidic.
Wow. Okay, so it's obviously a very serious issue, as demonstrated by the pictures of the mussels that didn't look as appetizing as they might have once done. You talked about potential technology to remove CO2, but at what scale do you need to do that to have any kind of impact? And before you answer that, the video that showed the corrosive nature, the red and the blue video, which projection line was that based on? Was that based on Paris? Was that based on worst case scenario? So if you could just help us understand those a little better. Thank you.
Yeah, sure. Sorry, I should have put that on there. That was RCP 8.5. So that was the kind of a high emission scenario for that one. But
Right.
Even under the 4.5 scenario, you get about 40 to 50% of the North Sea becoming corrosive seasonally. In some areas around the world, in coastal regions, we're already experiencing those sort of levels under today's CO2 conditions. In terms of carbon dioxide removal, yeah, it needs to be done at mass scale. It's not the solution. The only way to really reduce acidification on a global scale is to be doing switching from a carbon dioxide emissions system. Something like the Secure system, which is works-based, it kind of uses the fact that the marine carbonate system takes up CO2, and if we can take out that CO2 and capture it, and then essentially put that captured CO2 into locked storage, geological storage, then the oceans will then take up more carbon dioxide from the atmosphere. If those sort of systems are proven to work well and can be tagged on to things like desalinization plants, or again, kind of old oil rigs that are decommissioned, and you can sort of use those sort of systems, then across a global scale, they could account for about, I think it was, I don't have the numbers on top of my head, I think it was about 2% of the current emissions, but I would need to just double check that number. But it needs to be done again at a global scale to really have a significant impact. I think those sort of CO2 removal technologies need to kind of go hand in hand with all the other solutions.
Absolutely. And would the coastal areas recover as CO2 levels drop?
So yeah,
sorry.
No, that's yeah. I think we have to think of the oceans have a long-term memory. They do take longer to come back to kind of pre-industrial levels, for example. And I think even with the Paris Agreement scenarios, we're looking at maybe stabilizing at today's level rather than going back up to pre-industrial conditions. Certainly in the near future, I think it will take thousands or so years to get back to higher pH levels. But any of these other factors that we can reduce in the coastal regions, generally what we find is these enhanced acidification rates also are impacted by things like eutrophication or these added nutrients. And some of the evidence from the time series in Holland, in the Netherlands, has shown that actually when the EU's introduced some of their water quality policies, then you can actually see a change in the acidification rates as you go through time, as those kind of improve the quality of the water. So we know we can do these other things that will also help that kind of overall trend. So I think there's definitely ways we can make the coastal systems much better and improve quality. Yeah.
Brilliant. Helen, thank you again. Excellent. Right, we'll now move on to our third and final speaker, which is Professor Richard Thompson. Richard, welcome. Thank you for joining us. And Richard's going to talk to us about microplastics in coastal waters, sources, pathways, and solutions. So, Richard, 12 minutes or so, 10, 12 minutes, whatever you've got for us. And if I can just remind everyone to use the Q&A function if you have or would like to ask a question. Richard.
Can you see my presentation okay?
I can. Brilliant. Thank you.
Okay. So I want to talk about microplastics in particular, but one of the things that I really want to stress is that actually these are part of a continuum of different sizes and shapes of plastic, and it's maybe a mistake to pull one out against the other. So I'm Richard Thompson. I'm based at the University of Plymouth. My colleague Helen also down in Plymouth, along with the Marine Biological Association. I'm based at the University of Plymouth alongside the Marine Lab. I think the first point I'd like to make, although the focus of my talk tonight is on the microplastics, this is part of a continuum of different sizes. At one end of the scale, you've got pieces of plastic debris in the environment that are literally so big you can see them from satellites in space. Through the microplastics, and you see a picture in the middle of this slide of bits recovered from the River Tamar, near to me in Plymouth, right down to the nano end of the size spectrum, where most scientists working in the field believe there will be particles of plastic litter, but they're beyond the limit of detection. Very difficult for us to pull those back from an environmental sample. So it's a really diverse mixture of sizes and shapes and origins. Even if we just look at the very small pieces, the micro, you see here the diversity of different pieces, the river sample of different fragments of larger items on the top left. Top right, you've got the microbeads taken from cosmetics. The bottom left, you've got fibers from clothing. And then the bottom right, you've got pieces from tire wear abrasion. So it's an incredibly heterogeneous mixture. And that also influences our understanding of harm. It influences our knowledge about the sources and the pathways, and also, of course, the solutions. So we're not dealing with one thing here, we're dealing with many different things. If we think for a moment about the sources, and this isn't my own data, but it's a reasonable representation of our expectations, we see this broken down between the sources of all plastic to coastal waters, large and small. The large is shown in orange there. So by far and away, the biggest input of plastics to the open oceans and to coastal waters are these large items. They are also relevant in the context of microplastics because those large items of litter entering the environment today will become the microplastics of tomorrow. They will fragment into smaller and smaller pieces. So even if we could solve the problem of plastics entering the environment today, we would still see an increase in microplastics in the ocean over the next few decades because of the fragmentation of legacy items that are already sitting out there. Then the turquoise are the smaller particles entering the environment, tire wear particles, plastic pellets, particles from paints, particles from washing clothes. My one quibble with this figure from Eunomia in 2018 is that it doesn't actually show us the levels of confidence certainty. It shows us a measure of variability about the central tendency, but actually at the time this figure was produced, we got very little knowledge about the actual real quantities of tire particles, for example. And I'll come back to that later on. But it gives you a feeling that the big is important, even in the context of microplastics. These bigger items are very important because they will become the microplastics of tomorrow. So we need to consider the large items alongside the smaller items that enter the environment as small pieces. If we think about those large items for a moment, there's really clear, unrefutable evidence of direct harm in the sense of economic harm, harm to human health and well-being, and harm to wildlife. And I think that's really clear from a point of view of the larger items. If we come to the microplastics, the smaller pieces, I would draw your attention to this evidence review from SAPIA of microplastics in nature and society for a very comprehensive expert review. And it's clear that there's evidence of harm in the environment from microplastics. A lot of the evidence of harm is based on laboratory studies rather than direct observations in the environment. But the prediction that you see on the right-hand side, this modeling study from Everett, suggests that if we don't do something about the microplastics, the really small pieces, in the next 50 to 100 years, we will start to see widespread ecological harm in the natural environment. So some of the harm that we've seen in lab studies, we will see on a much wider scale in the natural environment if we don't start to take action. And of course, these really small particles are going to be almost impossible to remove. So having talked briefly about harm, the types of plastic and distribution, the question I often put to an audience at this stage is there enough evidence to take action? If there isn't enough evidence, what's the missing evidence? So what's the key evidence that we need in order to understand whether or not we should take action? Now, actually, I think to some extent, public policy and industry have now answered this question. The situation has moved on from 25 years ago when I first started working on this topic, when there was quite a lot of disagreement on the actual extent of the problem. Now, we might still disagree on absolute numbers or quantities of organisms that are harmed, but actually I think the consensus is that the current levels of accumulation are harmful. And indeed, we've seen that recently through the UN resolution to establish a treaty on plastics. So if we're agreed that there is harm and that we need to do something about this, it really automatically takes you to, well, what do we know about the solutions? What's the evidence base there? And largely, we know it's about designing and using plastics more responsibly. It's not about trying to ban them, exclude them from our lives. The challenge here, and to me, this is where the biggest evidence need, the most urgent evidence need, particularly given the pressing UN treaty on this, is that we've almost failed to move the dial on here since the 1970s, since the World Environment Day, when we kind of coined this concept of reduce, reuse, and recycle. The broad areas where we need to work are still about reduce, reuse, recycle. The challenge is the devil's in the detail. Is banning a drinking straw going to solve the problem? Probably not. Is it banning all plastic from the supermarket aisle? Absolutely not, because we'd see increased food wastage. Where does reuse fit in? How much can we reduce the usage by reusing plastics? Where does recycle fit in? What are the plastics where we can achieve greater circularity? And the level of granularity about these broad categories of things, the level of trade-offs between which plastics should be designed for reuse, which products should we design for reuse, which for recycle, which should we try to eliminate completely. We have very limited information on those trade-offs. And there's a real risk we could jump to solutions that might actually be counterproductive to have unintended consequences without that evidence base. It's somewhat guessing. If I just go back a second though to talk about the sources and the pathways, and there's a lot of confusion about these. I see a lot in the newspapers about wastewater treatment, for example, being a source. And here I've illustrated this with tire particles, but you could equally talk about sewage-related debris, things that are flushed down the toilet. You could talk about fibers from textiles. Wastewater treatment is a pathway to the environment. It's not the cause of the problem. If we look at the tire particles here, the source is the generation, it's the friction of the tire against the road surface generating particles, which with the data that we collected in this report for DEFRA can enter the natural environment through road water runoff. They can pass through wastewater treatment, and some will be intercepted, but some will still pass the environment, or they can pass into the atmosphere and be deposited onto the water surface. So there's a range of different pathways to the environment. It's important to separate those pathways in our thinking from the underlying sources. And if we want to tackle this problem at the heart, it's important that we recognize what are the interventions at source, as well as trying to catch it along its way to the environment. In essence, the key thing that I think we need to do, whatever the size of the plastic, is to do a much better job of thinking about designing products for life in service and end of life with a better environmental footprint. If you look at the legislation, which I was really pleased to see in the UK on the rinse off plastic particles to microbeads in cosmetics, some of our evidence at the University of Plymouth contributed to that legislation. And you think, well, that's a real triumph of science informing policy, and it is, except the patent on the use of these small bits of plastic was filed some 50 years previously. And so you ask the question, or I asked the question, did nobody at the design stage or the production stage ever ask the question, where are all these pieces going? Could we not have seen this one off the pass? So I think it's absolutely essential that we're thinking about the environmental phase right from the design stage. And yet, if I ask most product designers, whether it's microbeads in cosmetics or a humble lemonade bottle, they tell me that end of life is not in the brief. You could say the same thing if we look at the fibers of microplastic from clothing. And yes, you can catch them in wastewater treatment. Modern wastewater treatment plant is incredibly effective, but let's not forget that most of the global population are not connected to that level of infrastructure. And even when you've caught those fibers from clothing in the wastewater treatment plant, what do you do next? In many places, a logical use of that sludge is to return it to the land as a fertilizer. So you catch the microplastic and you put it back into the environment. Some would suggest, and the French are moving for legislation to fit filters on all washing machines. We've tested a range of devices. These in this example, retrofit devices. Some of them quite effective, but others hardly any effectiveness at all, and yet they're marketed with the consumer believing that they're doing some good by using them. So there's a real knowledge gap, I would say, about the efficacy of different types of solutions and those trade-off. And yet we've already got really strong evidence that actually changes in the design of the garment, the yarn construction, the weave, could actually potentially reduce microfiber emissions by around 80%. So again, I'm making the point of stressing it, that it's important to think about interventions all the way along that source pathway to the environment. But the place to start is at the design stage to see to what extent can we reduce plastic emissions, microplastic emissions by better design, something that's simply not been part of the design phase. And you could say that if we think of recyclability of plastic bottles, we're failing here, if I talk to recyclers, to design bottles, even of polymers that we know are highly recyclable, by incorporating colorings, which can halve the value of those bottles in recycling. And it's absolutely relevant to talk about those here because, as I say, those larger bottles will become the microplastics of tomorrow if we fail to create a circular economy for them. We know the polymer that's sitting in those bottles has a high potential for recyclability, high potential to join that circular economy, but adding those colorants reduces the value to the recycler by about 50%. So we've got to do a better job of designing for end of life. You know, we've known for 40 years or so that those bottles could have a value, and yet we failed to take that on board at the design stage. And I think the same is true when we look to biodegradables and compostables. They have a role in here too, but we've got to make sure that the consumer understands how to use them, that there's correct information, that this isn't about degradation in the natural environment, it's about degradation if those products reach a commercial composter, for example, with appropriate conditions of pH and temperature, only under certain conditions with the benefits to the world. So we need appropriate standards, and we need to communicate that to the consumer. And of course, we need a waste management stream that will collect separately then the compostable waste from the plastic bottles that you see on the left-hand side. So it's really important we think about these solutions in the round, and we've got the evidence to allow us to trade one off against the other. Where do we reduce? Where do we recycle? Where do we remove completely? Where do the biodegradables fit? So if I were to summarize where I think we are now, and where I would say we've changed over the 25 years that I've been working on the topic, I feel there is now broad scale consensus that actually we've got a problem, that the current situation is bad. And so even as an environmental scientist whose lab has been funded for 20 years to look at the problem at sea, I'm saying that's not the evidence we need in bulk anymore. There are I's we need to dot and T's we need to cross about harming the environment. But actually the bit that we're really missing, the bit where the dial is not moving forward, is about how do we trade off between these different solutions, these different categories within the waste cycle. Reduce, reuse, recycle. Where does education fit into this? Of course, it's really important, but unless we've got a joined up story about what the average citizen can do, it's quite difficult to know how to educate them, other than simply say, what we've been saying would keep Britain tidy for decades, just put it in the bin. And we need to move a step beyond that. We need reliable independent evidence to guide us towards that. Without it, we're resorting to guesswork. And my concern is that we could end up in a worse place. So we need to take this current momentum, and we need to make sure we've got the evidence base to guide us towards different appropriate solutions. And it's not to say there's a single solution, but it's about picking the right solution for the right product. It's also going to be about recognizing that those solutions will vary from one location to another. I mean, nationally within the UK, I think we're fine. But if I go to Indonesia, where I'm also working, you know, the main problem there is a lack of the waste management infrastructure. If I look outside my doorstep tomorrow, there's very good waste collection. It's what happens next and how to link that waste collection to the design that's maybe the missing. So that's more or less it from me. I would say if you want to dig more deeply into this topic, we're organising a side event at the UN Oceans Conference in Lisbon, where we'll be looking at what is it that's holding us back from solutions, the key science and innovation gaps that are needed to tackle this global environmental challenge. And if you want to find out more about the work that we do, then please Google the International Marine Litter Research Unit. Thank you.
Richard, brilliant. An awful lot in there. I let you overrun a bit. I apologise that it may have cut down our questions, but I think there was so much that was important to hear. One question from me is, in our last meeting, we looked at the decarbonising feedstocks in manufacturing by using alternatives to hydrocarbons in the production of plastics. Now, my chemistry knowledge is not sufficient to know, do you just create a different type of plastic that would end up in the oceans if you move to a biodegradable or a bio-based plastic? Does it still end up with small particles that don't degrade, or is it a completely different beast?
It's a really good question. And in essence, all you're doing is altering the carbon source from one that's petroleum based to one that's coming from a renewable feedstock. And it sounds really attractive. We're going to grow the plants and we're going to turn it into the plastic. But actually, the main, of course, would like to decouple the plastic from fossil oil and gas because it's a non-renewable resource. But it's the carbon that's coming from fossil oil and gas going to plastics, about 4% of world oil production. So it's relatively small. The main problem in the life cycle of plastics isn't at the beginning of the life, it's at the end of the life. And my overriding point here would be that you could switch the carbon to one that's coming from a renewable source, but that per se will do nothing to fix the problem of the waste that you're generating at the end of the lifetime. And actually, if you want to decouple yourself from fossil gas, what you really want to do is move towards a circular economy where we're using the end-of-life plastic to make the new plastic. That would decouple yourself from the fossil oil and gas as the carbon, but it would also decouple you from the waste, which even in managed systems is a colossal problem.
Yeah, and hence your better by design type plea. Brilliant, thank you so much. Right, we are going to move on now to questions. We've got half an hour or so. And just before I do that, actually, I have noticed that our former president and newly elected life member of the PNSC is with us, Lord Brewers, Alec Brewers. Alec, welcome, thanks for joining us. You're very welcome as ever. It's good to see you. But we go on with questions, and the first one is to Viscount Stansgate, our new president. Stephen.
Hello, and may I thank everyone for 3 tremendously interesting and varied presentations. I've got a quick question to all 3. First to Matthew, can you say a word about the unexpected problems you encountered when building the Thames Tideway tunnel? And to Helen, can I ask what links there are between the work you're doing and a biodiversity loss? Is there any involvement in the work you do with the COP15 conference that's going to be held in China later in the year? And finally, to Richard, in view of what you've said, do you foresee any role for future legislation in dealing with these issues? And if so, of what kind?
Great. So should we take those in order, Matthew?
Okay. Thank you for that. There's many ways I could answer that question. Unexpected problems. There are always challenges that you don't foresee on major projects. One of the challenges you have is you don't have perfect information when you set off. So, for example, there were a number of sites for probably good reasons at the time in terms of the sensitivity of engaging with those sites and those communities, where possibly there could have been more surveys undertaken. You know, so if you launch a big project, you know, you want perfect information, but that's just never going to be achievable. So I guess that there were certain sites where we discovered things we didn't necessarily need to discover, and it cost us more money and more time. And obviously on major projects, you know, time is absolutely fundamental in terms of managing your primary schedule and your critical path and avoiding those additional costs. So, but otherwise, other surprises, I guess, surprising in terms of financial markets as well. The macroeconomic conditions led to our financing probably outperforming our financing assumptions. That's before we even get onto a pandemic, which was in nobody's plans when we set off in 2015. And that led to about £200 million of extra costs for us, and sort of up to about 6 months on the programme.
Okay, thank you. Well, both Stephen and I are sitting only feet from where they hung the lime on the curtains.
Yes, the curtain.
So on behalf of the new generation of members on both ends of the building, thank you for everything. It's a fantastic project.
Brilliant. Helen.
So the links between our work on acidification and the biodiversity loss. So I personally won't be attending the biodiversity COP15, but we do have members at PML and also the wider Plymouth group, Marine Research Plymouth, that will be attending. We are very much aware and of the mindset that acidification and all climate stresses impacts the biodiversity issue, and the two do go hand in hand. So we have especially these projects that we've been looking at, where we're looking at, I mentioned climate smart marine planning, is a really useful way of trying to kind of match the two together. So if we're thinking, for instance, about where we put marine protected areas that will allow us to increase the biodiversity and assist with the biodiversity recovery, then we can actually make sure that we're taking into account these climate change impacts. So things like the acidification will be included in that. And we do that at very regional and local scales, so that it allows managers to really understand, and governors to understand, the issues that they need to deal with in order to plan effectively whatever maritime activities are ongoing. So there's things like that, that kind of work definitely feeds into each other. And I think PML and university and the MBA, Marine Biological Association here in Plymouth, I think there's potentially a side event will be, or there'll be side events at the COP15. I don't have the details to hand, but definitely look out for Plymouth University and MPA.
Thank you very much. It's very helpful.
Thank you. Richard.
So absolutely, there's a role for legislation. I think, you know, on the one hand, I'd say we can't ban everything, which often is a comment that I get kind of when I'm giving public talks, that can't we just ban it all? And of course, plastics have an absolutely crucial role. They have the potential to reduce our environmental footprint on the planet. It isn't that we shouldn't use plastics. It's got to be better by design. So banning will only take us so far. I think the challenges come where in the applications like the plastic bottles that I illustrated, where the plastic is the best material to do the job in delivering that lemonade compared, let's say, to glass or aluminium. But it's how do we then achieve the best, the optimum, if you like, will lead perhaps to circularity. So I think there are some perhaps fairly broad tools like mandating recycled content and increasing the requirement for recycled content that could be really quite useful to pull in the right direction. I think we need to avoid being tempted by the low-hanging fruit that perhaps falls within the short timescales, let's say, of a Parliament sitting. You know, it's always nice to have some wins, but I query how much banning drinking straws will achieve, for example. It's looking to the longer game. We've got to find ways to do that will also be popular and be understandable. So things like recycled content, working on mandating that. The industry will always say that they need to see a level playing field, and I think that is important. It may be overstressed at times, but one of the things that relates to that I think is going to be really important is that we need very clear standards on plastics, whether that's about whether or not they're recyclable, or whether it's about whether or not they're biodegradable, and if so, in which context and in which waste stream. So we need clear standards that are linked to clear testing, and then we need clear labelling that's associated with that, so that if the consumer sees it says it's biodegradable, they understand what that means. And with the sense of biodegradability, it's a system property, so you need to link it to the receiving environment. It's biodegradable in a commercial composter, or yes, this is natural, this will biodegrade naturally and harmlessly in the open environment. So it's about making sure we've got the messaging right, because I worry at the moment that we, to some extent, we see some greenwash that could actually be counterproductive, that could lead the consumer astray to thinking they were buying something that was environmentally benign, and yet actually it hadn't been properly tested. And I think we're going to need to rely on some of these terms to actually get the message home from an educational point of view. So it's really important that we've got some robustly standardized terms that can be used, and people will understand what those terms mean and can feel they can rely upon.
Thank you very much.
Thank you. Right. We'll move on to our next question, which is John Lowe. John, welcome. If you could just remind everyone who you're representing, actually, for all those who are going to ask a question, if you could just state which organisation you're from, that would be great. John, welcome.
Yes, good evening and thanks. Really exciting presentations, full of new information. I'm here for the institution of mechanical engineers, but also for private interests, in particular running an industrial museum. And Matthew, you'll be particularly interested that we are very good at promoting STEM. So it's promoting STEM to young people, but IMechE is I'm representing. And my question is, thinking about climate change, some predictions are that London will drown, and clearly if climate change does happen in its worst degree, there will be mitigating projects to do something about that, whether it's the Thames barrier or another one. However, how does the project you've described, how does that take climate change into account? Do you have to go back and do Thames Tideway Mark II, or is it there from the beginning? And do contact me about STEM later.
Thanks, John. Matthew.
Yeah, thanks, John. There were, probably going back 10 years ago or so, there were a range of different, probably longer than that actually, probably a range of different scenarios, climate change scenarios that were developed, and we tested effectively the tunnel against those different scenarios, and effectively changing rainfall patterns, which obviously impact on the sewer network. And effectively, the expectation is that the tunnel could be used more often. So at the moment, it's expected that the tunnel will be at full capacity, probably 4 times a year. And effectively, when it's at full capacity, then you wait for particularly Beckton sewage treatment works in the east of London to have treated the sewage that's arrived at the plant, and then when there is spare capacity, then pump it up basically from the bottom of the Lee tunnel. So effectively, the tunnel could be used more often, more frequently in different potential climatic conditions.
But the infrastructure doesn't need a retrofit. You don't have to raise the height of the vertical shafts of the defence mechanism around, for example.
That wasn't expected, no. But I guess it depends how extreme your scenarios would be.
I'm comforted by the planning. Thank you, Matthew.
Great, thanks, John. Next, we will go to I think it's Dr. Ruth Thurston. Ruth, hi.
Hi, thank you. That's really interesting presentations, and so thank you very much. I've got a question for Helen, if I may. You mentioned enhancing sort of blue carbon to mitigate ocean acidification. So given how much of these types of habitats that we're talking about shellfish habitats like mussels, also the native oyster, we're talking about kelp and seagrass. We're beginning to understand just how much of that habitat has been lost over the last few decades and centuries, largely since the Industrial Revolution. Unfortunately, most marine, so we're going to need active restoration to do that, but most of these are currently very small scale. I wondered if there's any consensus as to what scales of habitat restoration are needed to contribute measurably to sort of, mitigating ocean acidification trends.
Yeah, so I think in terms of specifically for ocean acidification, some of these restoration projects are still relatively new in terms of understanding exactly how they will help to mitigate acidification. So we know, for instance, that seagrass meadows or algae, kelp forests, things like that, the photosynthesizers, the plants will take up the carbon dioxide more rapidly and potentially secrete that carbon dioxide away. And that has 2 effects of reducing the carbon dioxide levels, but it also locally can actually increase the pH, and that can help to allow species around them so other organisms that are living around those habitats to benefit from enhanced pH. But it's still very, very early days in terms of knowing exactly how that carbon stays locked away, but also what the footprint is of these sorts of habitats, how quickly does that carbon change if you've got a tidal system, for instance. So the coastal understanding of acidification is really still at the stage where we need to understand a bit more about what's going on. There was a recent report that came out this year, not that long ago, called a research strategy for ocean-based carbon dioxide removal and sequestration. And that was written by the National Academy of Science, for the National Academy of Science, Engineering and Medicine. And it kind of put into perspective some of these different ocean-based activities, including things like renewing ecosystem recovery and seaweed cultivation. And they suggested that there was, in terms of the durability of something like ecosystem restoration, it was a very good outcome. It was a good thing to do. We could expect to have kind of 10 to 100 years worth of removal of CO2 in the sort of short term, or more than that in the long term. But in terms of scalability, we're talking about less than probably 1 gigaton of carbon dioxide per year. So we would be talking about significant amounts of space. Having said that, like you pointed out, because there's been so much degradation, any opportunity to improve that degradation is going to improve the ecosystem health, and that has knock-on consequences for acidification. But I think that we're still a long way off from putting a kind of number of, like an area of habitats that's required for that.
Thank you, Helen.
Thank you.
Excellent. Right, and last question, it would appear at the moment, is from Alec Brewers, Lord Brewers. Nice to see you. We'll hear you.
Can you hear me all right?
We can, thank you very much.
Oh, excellent. Well, Stephen, I think you've organized an excellent session here. The presentations from Richard and Helen, however, quite disturbing and worrying. Matthew's quite encouraging in many ways. I've watched this tunnel all the way, and I have two quick questions. First for you, Matthew, what do you expect will limit the lifetime of the tunnel? I think you mentioned something in excess of 100 years, was it? But what is it that will limit its life?
That's right. The minimum design life of the tunnel is 120 years. And as part of that, to support that, we put in the secondary lining as well, which does help with stopping sewage leaking out of the tunnel, but also water leaking in it. But it does provide that additional certainty around the durability of it. The other answer to it really is the fact that we, as an organisation, Bazalgette Tunnel Limited, we were created for the construction phase to deliver the tunnel, but there is an ongoing responsibility. We will, whilst we hand over above ground assets to Thames Water to operate, we will continue to own and have responsibility for maintaining the deep shafts and the tunnels. So there are likely to be 10-year inspections to continue to sort of look after the tunnel. I can't give you a much more specific answer than that, apart from probably whatever impacts the longevity of concrete.
How long do you think Bazalgette thought his tunnels were going to last?
Goodness me. Good question. Good question. I don't think he was challenged about longevity, was he? Just about sorting out the solution. But it's interesting to see that 150 years on, I mean, he transformed obviously large parts of London as well.
Yeah, I was rather hoping that I bet he would never have bet that was going to happen, and I hope you're wrong in thinking of 100 years. Maybe it'll be 300 years.
Well,
that is if we haven't died from all the other things. At any rate, I think it's a magnificent project, and I'm so glad that we went ahead with it. Richard, my question for you is, collecting these plastics seems an extraordinarily difficult thing to do. And I was just wondering, as a simple question, is there a way of enhancing the precipitation of these small plastics in a liquid? I mean, one does it electrostatically, I suppose, if they're airborne, but underwater, what do you do?
Yeah, I mean, so the first point I would go to, you said you found it depressing or worrying, and of course it is, but I see this very much as a glass half full, because in difference to the ocean acidification and the carbon emissions discussion, where the emissions are directly linked to something we want, the heat, the transport, the flight, whatever. In most cases, we could have the benefits of plastic without these emissions to the environment. So I definitely think it's something we can fix, and I wouldn't want the audience to be depressed about it. I see it as a glass half full. If I had a rich philanthropist that sort of phoned me this evening, or a rich prime minister, and they asked, where do I spend my money? I would say at the moment, I would rather we spent 95% of that resource on turning off the tap, rather than trying to sort of extract it after it's escaped to the environment. And that's not to say I don't think there are answers there, but I think that the most efficient place to focus our energies and our limited research budgets are on reducing the emissions in the first place, the fibers from clothing, the microbeads and cosmetics, the tire particles, okay? And we've seen big investment in coastal cleanup operations and swinging booms and all kinds of things, trying to suck it back from the environment. And I think it's, as we start to turn off the tap in terms of the emissions, then I think we can afford the luxury of spending more on cleanup strategies. Yes, you can remove by electrostatics when it's dry, you're absolutely right. And we've tried that in terms of separating from sand to count the stuff in the first place. But of course, damp is going to hinder that. You look to, I think, the second or third slide that I showed with the heterogeneity, the variability of the particles. Even just the tire and road wear particles are varying by orders of magnitude in terms of their transport potential. Some of them have got bits of road grit attached to them. Some of them don't. Some of them are incredibly fine. Others are quite coarse. So I think we've got quite a challenge. That's not to say we couldn't develop improved techniques for screening it out. But even if we've got them, and there, just finally, I'll go to the wastewater treatment example, where a good wastewater treatment plant could probably remove in excess of 95% of the microplastics that are going in. But what do you do with them next? And they're mixed with some more valuable solids that could be used as a nutrient enrichment. So I think the challenge is pulling out the particles that you want to remove and leaving in behind the ones that you want to stay. And then what do you do when you pull them out? So I'd spend my money on trying to solve it from the source as much as possible now, just because of the limited time and resource we've got.
Thank you.
Brilliant. Thank you very much indeed. Well, in the absence of any further questions, I suppose we can wrap up. So can I just say a huge personal thank you to our three speakers, to Matthew, to Helen and to Richard. I think your presentations were very informative and also very diverse, very different, giving us different perspectives on this issue of what can we do to improve coastal water quality. And as Alex, excuse me, Alex said, some positives and also some warnings in there. I think I'm glad to hear, Richard, that you think the glass is half full and that there's something we can do about it. I think my own personal view is that I think there is an appetite for people to want to do the right thing if we can get them to do, get them the right information. And that's perhaps a discussion for another day about who takes on that role and how we do it on a practical basis to allow people to make the right choices. But for now, a fantastic evening. So can I thank our audience and our questioners for your inputs and for your attendance. And of course, I want to thank the PNSC team, Lee, thank you very much. And of course to Karen Smith and to John Slater, to Ben Allen and Alfie Hoare, who will be writing up the account of this evening to go in our or to go on our website, but also to go into our quarterly magazine, Science in Parliament, which is now distributed, as I hope many of you will know, to all members of the House of Commons and of the House of Lords. So, you know, it's people wait with bated breath for its quarterly publication, because it is the definitive account of how Parliament and science interact. So people do actually look forward to seeing it. So I look forward to seeing the next edition with your contributions in it. For now, that's it. Other than to say, I'm delighted that our next meeting will be back in person. It will be here in Parliament on Monday, the 4th of July, Independence Day, independence from the COVID restrictions. We're going to be back face to face. We're meeting at 5:30, and it's bound to be an absolutely fascinating discussion, one which I hope someone will help me understand, because it's on quantum technologies and the future for the economy, society, and security. I mean, I've been very fortunate. I've had briefings from some real experts on quantum, but there are still areas of it that I find very difficult to get my head around, particularly around entanglement, which is, my understanding is the ability to be in two places at once, basically. But I'm sure it will be a fascinating meeting and will answer some of those questions. And that is being held in partnership with Imperial College London. So I very much hope to see you all there. Karen, will we be seeing you on the 4th of July? Good. In which case,
yes,
I'll have something to say then. And it's great to see you, by the way. It's great to see you face to face. So thank you for all your help this evening. That's it, really. I hope you've enjoyed it as much as I have, and I very much look forward to seeing you at the next Parliamentary and Scientific Committee discussion. Until then, have a good month, and we'll see you all soon. Cheerio.